So let's recap a bit. We studied two settings for cryptography. First, we looked at the symmetric setting and then the asymmetric or public key one. In both of them, we provided means for parties to encrypt or authenticate communicated data so as to provide both integrity and privacy. The difference was in the types and nature of keys that they had to do this. In the symmetric setting, it was assumed that they shared a common secret key, while in the asymmetric setting, the assumption was that one party, Bob, had a pair, a public key and an associated secret key, retained the secret key, and disseminated the public key. We then turned to the question of how we actually arrive at these keys, which in our earlier study were just magically assumed to be present. And we studied the public key setting, namely how to realize a setting like that. And we saw that the difficulty was for Alice to know that the copy of Bob's public key she has is authentic, and how to achieve that through the public key infrastructure and certificates. So now we're going to turn to the symmetric setting, namely we're going to ask how to realize that. How do we arrive at a situation where Alice and Bob both share a common secret key? Now the first question we may have about that is, why bother? We can, using public key cryptography, already encrypt and authenticate data using public key encryption and signatures. So, and as long as we have a way to realize public key crypto, why would we need secret keys at all? The fact is that the way communication happens over the internet through protocols like TLS, your data is symmetrically encrypted. So TLS aims to put you in a setting where the client A and server B share a common key K, and then an authenticated encryption scheme is used by either party to encrypt data, generate a ciphertext, then to the other party who decrypts. Remember, an authenticated encryption scheme is the symmetric primitive that provides both authenticity and privacy, and is kind of the main end tool created by symmetric crypto. Now, this doesn't mean that public key crypto is absent. In fact, it's used in a very important way in the TLS handshake. And what that does is a session key exchange. The job of this handshake is to provide Alice and Bob with the shared symmetric key, which they will then use in this fashion. And so the protocol to do that is called a session key exchange. Now, one may again ask, but why do this as opposed to just directly encrypt and authenticate with public keys? Well, one reason is performance. Symmetric cryptography is much more efficient than the number theory based asymmetric, and we desire speed over TLS connections. But perhaps even more fundamentally, it reflects the architecture of internet communications, where parties engage in different communication sessions which can have durations ranging from short to long. And many of these sessions are happening concurrently, as represented, for example, simply by all the different tabs in your browser, some of them being tabs to the same website in which you're just conducting different transactions. And the purpose of the session key exchange and this whole paradigm is that each such session, communication session, gets a fresh shared symmetric key. It gets a key that's independent of all other sessions, so that security of one session becomes independent of that of the other. And this is how, in fact, TLS and internet security operate. All right, so let's then turn to this task of arriving at a shared symmetric key, a session key that should be unknown to the adversary, but known to both the legitimate parties. Well, we have a tool we've already studied which seems to do that very well, which is the DiffieHellman key exchange protocol. So here we fix a cyclic group. We know its order and we know a generator. And we assume the computational DiffieHellman problem is hard. And we also fix a hash function, which returns strings of some length k, which will be the length of the key that we get back. What Alice does is it picks a random exponent, little x, raises g to that power in the group to get big X, and then tells Bob, hey, I'm Alice, and here's my quantity big X. Bob does symmetrically likewise, picks an exponent little y at random, raises g to that power to get big Y, and says, hi, I'm Bob, here's my quantity big Y. And now, as we know from that nice algebra, the quantity g to the power little x times little y is something that Alice and Bob can compute through these two different mechanisms, one taking the public quantity of the other and raising it to their own secret power. And we'll call that quantity L. Now, you could maybe think of L as the shared secret key, but really what we do is we hash it down to get a string of the desired length. And that'll be the key arising out of this protocol. And now we can ask ourselves, are we done? Have we solved the session key exchange problem? And do we have a nice means to arrive at a secret key? And indeed, we seem to have suggested so in the past. Why did we do that? Because this protocol has the important attribute of being secure as long as we measure security relative to passive adversaries, meaning ones that observe the communication. Such an adversary acquires big X and big Y and aims to compute K, which is the hash of g to the power xy. The main element of this, of course, is computing g to the power xy itself, because the hash function is public, and doing that requires solving the computational DiffieHellman problem, which we've assumed to be hard. So our takeaway is that at least for properly chosen groups, the DiffieHellman key exchange is secure under this type of passive attack. The difficulty is that those are not the types of attacks that we're really concerned with. We're concerned with, again, these entity in the middle attacks where the adversary simply pretends to be B, and the real B may not even be in the picture at all. So when Alice says, hi, I'm Alice, and here's my value big X, it's actually the adversary who responds and says, I'm B, falsely claiming that identity, and here's my exponent, here's my group element big Y. The way the adversary picks these is simply by following the protocol. She just does what the protocol says, pick a random exponent little y, raise g to that power to get big Y, and send that across. But since the adversary knows little y, it can compute the DiffieHellman key L by raising big X to the little y. The result of this is that while the Alice entity thinks that it shares this key K with Bob, in fact, it shares it with the adversary. And now if A encrypts information under K, her sense is that that message is intended for Bob, who is the person she wants to be able to see it and decrypt it. But in fact, the adversary is the one who can decrypt it and recover the message. So in summary, DiffieHellman key exchange doesn't solve the session key exchange problem due to this entity in the middle attack and the lack of authenticity, and other reasons as well. But it's not something we're going to abandon. What we'll see moving forward is that it's actually a useful and important tool in achieving some properties that are now considered mandatory for session key exchange, in particular the property called forward security. So DiffieHellman will be back. Let's now talk a little bit more about the goal here, which is session key exchange. Now, in the past, whenever we've introduced new primitives or goals, we've done it through a formal syntax followed by a security definition that uses games, and we've carefully defined and formalized everything. We're not going to take that path with session key exchange, mainly just because it's significantly more complicated and it's harder to write down games and that capture all our requirements in the way we want. So our discussion of this topic will be more example-based and illustration of ideas. So what we're going to consider is what would be called in this domain unilateral public key-based session key exchange. This reflects a TLS type setting where the server B has a certificate and thus corresponding public and secret keys, but the client A is not assumed to have a certificate or corresponding keys. The purpose of the protocol then is to generate a session key which should be known to both A and B, and it has very roughly two main requirements associated to it. The first is authenticity. So A should be convinced that it shares K with the identity B, not with some other entity. Since this is unilateral, there isn't anything in the opposite direction. So B is not expected to know from this that it shares a key with some identity A, or at least in the sense that it's authenticated that identity. And the second requirement for the session key is secrecy. Your adversary shouldn't know the value of the session key. Again, this is the most common setting for TLS, where B is a server like google.com and A is a client. And now in TLS applications, the client does authenticate itself, but the way it does that is over the TLS channel as part of the application, for example, by flowing a password. And so from the point of view of the session key exchange in TLS, that is not something we're concerned with. Now, these requirements are quite complex when you actually get into them. For example, secrecy and authenticity must hold even when the adversary knows session keys of other sessions. So there are many sessions going on. All of them will be producing their own session keys, and no session key should influence any other. Also, the adversary here must be active, as in the entity in the middle attack. In fact, we will assume the adversary is in complete control of communication. When you think of sending a flow to another party, what you're actually doing is handing it to the adversary, who will decide where it goes. Furthermore, there are many other requirements that supplement these basic ones, including forward secrecy, anonymity, and others that we can consider. Now, while we won't get into the definitions in a great deal of depth, it's at least worth commenting a little bit about how we capture and model the secrecy requirement. And whereas earlier it was alluded to as saying the adversary cannot come into possession of the session key, the actual requirement in the formal definitions is stronger, that it cannot even distinguish the true session key from a random string of the same length. So how might that work? What you imagine is that the protocol terminates and one of the parties outputs a certain session key, saying this is what I think is the session key. What your game does now is it picks a random challenge bit little b, and it then defines two keys, K1 and K0. K1 is this actual session key. K0 is simply a random independent string of the same length as the actual session key. And then the adversary actually gives to, the game actually gives to the adversary one of the two keys, K1 and K0, depending on the challenge bit. So it says, here's K sub B, and it says, can you tell me whether I gave you the real session key or an independent random string? And the adversary tries to guess that by outputting a bit B prime, and its advantage is the probability that it guesses correctly scaled away from 1/2 in our usual way. So again, the requirement then would be that this adversary's advantage be small, but that should be true even if it has obtained session keys of other instances. The only session key it's somehow not allowed to have obtained is the one of this party X in this session, and the one of what's called its partner, the entity with whom it shares it. Now, defining partners is complex, and that's one aspect of the formalism we're not going to get into. And again, this must hold when adversaries are active in charge of all communication. And as a warning, this is not a full formal definition. It's just a small sense of some of the ideas behind it. So what's going on with session key exchange? It's an old problem, and over time people have recognized that it's really quite subtle and difficult. It's easy to specify protocols. They tend to be little 3-4 round things, but it's quite challenging to get them right. And over time, many attacks have surfaced, and many different security requirements have emerged, and many protocols claiming to achieve them. It took some time before a modern cryptographic definition and provable security treatment emerged, but that came in the early 90s. And since then, there's been quite a bit of progress in that dimension. And nowadays, these formal definitions and proof-based support are in fact how we look to design session key exchange protocols and what's sought in ones that are standardized. The TLS most recent 1.3 version session key exchange is designed in this way through formal definitions and proofs, and is based on Kravchik's Sigma protocol. So as indicated earlier, we're just going to take a kind of example-based walk through session key exchange, just trying to show you what protocols look like, illustrate some of the issues, maybe a few of the attacks, things like that. So let's start with this, where here we have our Alice, the client, and Bob, the server. Remember, in our setting, Bob holds a certificate, Alice does not. They want to arrive at a joint session key, and the client contacts the server and says, hi, here's my identity, Alice, and here's a quantity we call a nonce. This nonce R sub A for random is randomly chosen by Alice, and its intent is to create freshness. It's saying this is a quantity new and fresh to this session. Any other session would have its own nonce, and this is how we're going to make this session unique. The server says, okay, let's start the protocol. Here's who I am. I'm server B. Here's my nonce. I also pick a random number B. Here's my certificate for authentication. And as proof that I really am B, I'm going to sign our nonces. So sig bx here is B's signature on this quantity here, the concatenation of the nonces. That will, of course, be computed under its secret key that is associated to the public key that's in its certificate, and which can be verified given that public key. It will use any of the many signature schemes that we've studied before. Now, when writing these protocols, a lot of the steps and checks are actually omitted just for reasons of space and to avoid too much detail. But an important step here is that on receiving this, Alice actually verifies the signature using the public key inside the certificate. And if the signature does not validate, she's going to stop the protocol. Alice will also check the certificate. It's assumed here that she has the CA's public key. She uses that to validate the signature in the certificate. She performs all the required checks on it, the expiry date. She checks that the identity B matches that of the intended party to whom she wants to communicate, and whatever else. Once Alice is satisfied, what she does is herself picks at random a quantity to serve as the session key. So here there's a typo. This key is not chosen by B, it's chosen by A. Let's pause to make that clear a little here. So having chosen that to function as the basis for the session key, Alice needs to convey it securely to Bob. How does she do that? She encrypts it for Bob, and that encryption is performed under Bob's public key. So the certificate includes Bob's public key, and we assume it allows both encryption and signature, and here we use the encryption capability. The ciphertext encrypting it that Alice generates is simply sent along to Bob. However, we need now to authenticate this ciphertext, and what Alice does for that is use a MAC. Remember, a message authentication code is the symmetric primitive for authentication. She authenticates not just the ciphertext, but its association to the nonces, so that she's tying that ciphertext to this particular session to ensure freshness. What key would she use, however, to perform that MAC? It needs a key that's shared between Alice and Bob. Effectively, she uses the same key L here again, right? But in order to make sure that there isn't kind of confusion and insecurity created by multiple uses of the same key, what we actually do is, starting from this key L, we derive a MAC key by hashing it under a public hash function h2, and that's the key used here. And the session key is not actually L itself, but the result of some other different hash function applied to L. In this way, the K and the M keys are not related to each other, although they are derived from higher level key L. Okay. So again, in summary, nonces to ensure freshness. The server authenticates itself through its certificate and a signature. The client picks the session key through a random choice of L, which it sends over encrypted. The client authenticates the ciphertext and ties it to the nonces for freshness through a MAC. The key that the protocol produces, the session key, is a hash of L, and the MAC key is another hash of L. Many steps omitted. For example, here, the server would decrypt the ciphertext using its secret key, this one over here, recover the L, recompute K and M, use the M to verify the MAC, and only then say, okay, I'm happy with K as the session key. So we could look at this and stare at it quite a bit. There's a lot of stuff going on, much more than is visible from this short discussion. Indeed, once you start examining it, there are issues that arise. And so what I want to do is illustrate an attack on this protocol, which we call the identity misbinding attack. What this allows is a kind of mismatch between what people think of as the identity they're authenticated with and sharing the session key with, and what's actually happening. So here's how it works. The client, let's say, starts a communication session and sends to B an initiation request saying, hi, I'm A, here's my nonce, let's get a key. The adversary intercepts this. Remember, our adversaries are in complete charge of all communication, so they get this flow. And so far, B has seen nothing. The adversary then contacts B, and it uses the same nonce, but it makes this one change. It puts its own identity here, not Alice's identity. And after that, all it does is it forwards flows. So what does B do here? It says, okay, here's some entity called E asking to start a session. That's fine. I'm going to start a session with E, and I will do what I'm supposed to do. Here's my identity, my nonce, my certificate, my signature. E simply forwards all that over to A. A looks at this and says, well, that's fine. That's what B is supposed to send in response to my request here. So let's keep going. It continues with the protocol. It creates its ciphertext by picking L and encrypting it. It creates its MAC, all as before, sends that over. And again, E does nothing other than forward it back to B. What will B do now? It will accept this. It will take the ciphertext, decrypt, get L, check the MAC will verify, everything is dandy, and it will accept and say, oh, I have a session key K. What's the difficulty is that B thinks it shares the session key with E because E is the entity named over here. But A thinks that that same session key is shared with B. And so you have this incongruity or difference in who the parties think they share the same key with. And this is a problem. Now, what makes this kind of subtle and interesting is that it's not necessarily obvious whether this should be viewed as a problem or not. One reason is that you notice that our adversary does not know actually the value of the session key. To do that, it would need to decrypt C, which would require knowing the server's secret key associated to the server's public key, and it doesn't know that. But even though the adversary doesn't actually know what the session key is, there's something wrong with this picture, this misbinding of identities. And over time, cryptographers have decided that they view this as an attack that they would prefer to not see happen. And they tend to craft definitions that rule it out. So the understanding we gain from this is when we have a good protocol, it should ensure that if entity A accepts B with a certain key, then who B accepts can't be someone other than A, right? Now, note that the authentication is unilateral, so we can't say for sure B accepts A. But what we can say is that B either accepts A with that key or simply rejects, that it doesn't associate anybody with that key, and that's not what's happened here. All right, so maybe we could fix this, and the way that historically that's been done is to understand that we need to authenticate not just nonces but identities of parties in the signatures and MACs. So the protocol could be extended. Alice first sends the same stuff as before. Bob responds the same way. The change is in the scope of the signature. You have not only the two nonces, but the identities of the parties. So now Bob is saying, I not only confirm freshness, but I confirm your name as received here and my name here. Okay? And that continues. When the MAC comes across from Alice, it will include in its scope the names of the parties. And it turns out it's also important to add a confirming authentication from B, which is a MAC including the names of the parties, because otherwise you can kind of do identity misbinding again. Again, the way you get the keys is, remember, there's always a session key produced. That session key is a hash, which is applied to the key that A has picked over here, L. You may somehow think in some sense that L is in some sense the session key. It would be what TLS calls the pre-master key or something like that. But the real session key is a hash applied to L. And the MAC key is also a hash applied to L, but it's important that the hash function is different. And also, for good measure, we'll throw into the scope of the hash the names of the parties and the nonces. Now, I'm not going to claim that this protocol somehow works in some formal sense. I'm only still presenting it as a kind of candidate that has many of the properties that we'd like. So already, hopefully, what you can see from here is that session key exchange is a subtle problem, and protocols have a lot of different elements that interact together in complex ways. Now, as if that wasn't enough, we're now going to point to another weakness in the protocol, even as we've just defined it, so not with regard to identity misbinding. And weakness may not perhaps be the right term. Maybe a better term is an illustration that we'd like a form of security that we haven't discussed and goes beyond what that protocol provides. So let's see what the issue here is. So let's assume that the protocol as we discussed it has happened and been executed. And this has all happened correctly, and the 4 flows we saw have been sent back and forth, and now Alice and Bob are in possession of their joint secret key K as computed by the protocol. Our adversary here has done nothing more than record these flows. It hasn't been active. It's just eavesdropped, and it has a record of everything that was sent. Now, Alice and Bob, however, will start using the session key. After all, that's why they got a session key. There is some kind of authenticated encryption scheme, which under that key K would take some message X and produce a ciphertext, and that ciphertext would then be communicated by B to A, and A would decrypt it and thereby arrive at the message X. And this may happen many times because once you have that session key, you probably use it to encrypt and send back and forth a whole bunch of stuff, as happens in TLS. So suppose on a certain date our adversary records all these flows, not only the flows of the protocol of the session key exchange here, but this ciphertext over here. At this point, the ciphertext is extremely unhelpful to the adversary. The adversary wants to know what this message X is, but it doesn't know what the key K is, and this session key exchange being secure means it doesn't really have a good way to arrive at that key K. That would require breaking security of various primitives used in here, in particular this encryption. So she has no particular way to exploit the possession of these flows. But now suppose that sometime later, like a month later, something happens which allows the adversary to compromise the server's system. So maybe the server is infiltrated in some way and its keys are compromised. Remember that the server has a certificate, and that certificate includes its public key and associated secret key, and that is used for this signature over here and also for the encryption over here. We're now assuming the adversary actually acquires this secret key. Well, what happens? Well, first off, of course, the whole PKI system will kick in. So B will hopefully recognize that there's been a breach, will revoke the certificate and thus the public key. And the result of this is if Alice is in possession of the certificate revocation list, she will no longer try to make connections to this server. And so the ability of the adversary to exploit knowing this secret key appears to be curtailed. You would say, okay, the adversary got that key, but so what? But something else is possible for the adversary now. What it can do is say, remember, a month ago I had recorded all of this. So let's go back to that. Having this secret key, I can reverse this encryption the same way that B did to acquire L. And having L, I can of course hash it and obtain the session key K. Our adversary now knows the session key. If so, it can decrypt the symmetric encryption under K, decrypt the ciphertext that is, and it can recover the message X. So through these steps, our adversary will actually defeat the privacy requirement here and recover the message. And clearly that's not something we want. And we call this a violation of what's called forward security, right? And the interesting thing about it is how the long-term secret keys of B, having been compromised, results in a loss of privacy for information that was communicated possibly a long time in the past, right? So the damage done kind of percolates back through history. So what is forward secrecy then? It's the requirement that this not happen. In other words, it's a setting which says we are worried that the long-term secret key corresponding to the public key of the server Bob may be exposed because we know that servers are breached and all kinds of things happen. And we want to mitigate the damage caused by that by ensuring that it doesn't allow recovery of things that happened before that exposure. It doesn't allow recovery of session keys which were exchanged and used before this exposure happened. So interestingly, the way you achieve this is by integrating a DiffieHellman key exchange into our session key exchange. Now, this isn't merely some kind of esoteric concern. It's considered important enough that any modern session key exchange protocol will try to achieve forward secrecy. And in particular, TLS does do that. It's for this reason that you might see the term authenticated DiffieHellman key exchange. That simply refers to session key exchange with forward secrecy. Okay, so let's try to make this happen. So what we're going to do here is take our prior protocol and add forward secrecy through a use of the DiffieHellman key exchange. Now, interestingly, that will actually both strengthen and simplify things a little. So we're in the setting where, again, we fix some cyclic group. We have its order M, which is public, and we have a public generator. We assume the computational DiffieHellman problem is hard. Remember that in our protocol KE2, there were nonces, RA and RB, chosen by the parties. The role of the nonces now is going to be played by random group elements. So what A will actually do is pick an exponent little a at random and generate g to the power little a and send that across as her nonce. When the server Bob gets that, as per the prior protocol, he generates his own nonce, but now the nonce has the form g to the b, where the little b is chosen at random by Bob and thus known to Bob. The rest as before. Here's Bob's certificate, here's its signature, and as per the prior protocol, the scope of the signature is the two nonces, now these quantities, and the identities of the parties. Now, once this has happened, notice that both A and B are in position of g to the A, g to the B, and each knows its own secret exponent. So at this point, a DiffieHellman key exchange has actually been accomplished. And that means that if you consider the quantity g to the power AB, which we'll call L, the DiffieHellman key, both A and B at this point can compute it, right? A does it by raising g to the B to her exponent little a, and Bob vice versa. So they do that. They arrive at this DiffieHellman key, and from it they obtain two keys, one the session key that they want to agree on, and the second the auxiliary MAC key that helps them complete the authentication part of the session key exchange. They are all defined by hashing the DiffieHellman key. So this is a hash of L under one hash function. The MAC key is the hash of L under a different hash function. For good measure, they also include in the scope of the hash the identities and nonces. Of course, these are public quantities, but they manage to effectively personalize and tie to freshness these keys. Now we go back to the protocol. Remember that in the prior protocol, the last flow from Alice, or the last from Alice, which is the third in the protocol, was a MAC under this key M of the nonces and identities, so that's provided as before. And we had a fourth flow, which was a MAC back from B of the same kind of stuff. Now what we do is we don't put that as a fourth flow, we actually move it up here into the second flow. So that happens already over here. Why is that possible here and not before? Because here the server can derive this key M already at the time of its second flow, which it couldn't do in the prior protocol, which is one of the kind of nice things about the DiffieHellman based version of the protocol. As usual, there's a lot of stuff stuffed under the rug, in particular verifications. A here needs to verify the signature, needs to verify the MAC, needs to verify the certificate. Over here, Bob needs to verify the MAC. And they agree on K as a session key only if all this stuff works out. Okay, again, one needs to stare at this protocol a fair amount to understand what the different quantities are, how session keys are computed, what's going on, what its security may be. And although it has only 3 flows, its analysis is very involved and complicated. It takes a lot of definitions and a lot of work and judgment and reductions and all kinds of things. Our claim is that this kind of works. Let's maybe just illustrate a few elements of it. Remember that the goal we wanted was forward secrecy. And remember that what allowed forward secrecy to be compromised in the KE2 protocol was that when the adversary acquired B's long-term secret key, it was able to decrypt a certain ciphertext encrypted under B's public key which contained the value L that led to the session key, right? So that decryption, the reversal of public key encryption, was crucial to violating forward secrecy. What we notice about our new protocol is that actually there's no public key encryption used at all, right? You look here and no enc under B's public key ever appears. The only use of public key cryptography is a signature over here. So this very much reduces what B can do when it E can do when it acquires B's secret key. All it can do is forge signatures. There's nothing to decrypt to obtain the session key. And although forging signatures might cause damage, that ability ceases once the certificate is revoked. So it has a relatively smaller scope for impact. When the adversary compromises B to obtain the secret key of B, it would like to recover L, the DiffieHellman key, because that's the route to recovering the session key, which is a hash of L. But it doesn't have a way to do that, because to do that, it would need to solve the DiffieHellman problem here, the computational DiffieHellman problem. To derive L, well, L is g to the power AB, and it has g to the power A and g to the power B. How is it going to get L from them? So in this way, we feel like this is moving along to provide forward secrecy. And indeed, something like this is the core of the unilateral, which means server-only authenticated session key exchange in the TLS 1.3 handshake. And that's based on this Sigma protocol. All right. So again, this is kind of just a story about session key exchange, a very whirlwind tour through a few examples done at a very high level without any formal claims that they meet any formal definitions or proofs thereof. And in this same vein, sort of to illustrate different issues and problems in this domain, let's talk about another one, which is the use of passwords to do session key exchange. And in order to motivate and introduce that, maybe we should back up a bit and just talk a little bit more about passwords. They would be a great topic in their own right as one of the central mechanisms for security in the current ecosystem. But we'll talk about them just a little bit. So what we mean by a password is a human memorizable key, usually. Although, of course, you may have your password manager memorize it instead. And the feature they have is there's a tendency of users to pick relatively guessable passwords. Formally, that it's possible for an attacker to create a set of candidate passwords, call it D for dictionary, such that many times the passwords of many users would fall in that set. For example, this set would contain all common names of people, all English words, names of different sports teams, basketball and football teams, things like that. And if a user picked a password from that set, well, then it would be in this set. Now, the attacker calls that a dictionary, and through that may have a means to recover your password. Suppose you picked a password in this dictionary. That alone doesn't allow the adversary to recover it because it doesn't know which one in the dictionary it is a priori. But suppose that for some reason there's a certain public function f whose result on your target password is actually available to the adversary. And we'll see many ways that might happen, but at the moment it's an assumption. That gives rise to what we call a dictionary or brute force attack, in which what the adversary does is cycle through all candidate passwords in the dictionary, apply the public function f to each candidate, and test if it gets back this value that it knows, which is the result of f to the target. And when they match up, it decides most probably that is indeed the target password, and so it recovers your password. this is possible because these dictionaries are actually not too big. They're kept small enough that you can exhaustively search them. Now, these passwords are in widespread use. If you are using Gmail or internet banking or have accounts at pretty much any internet service, you're likely to have a password associated to do them. Indeed, most of us have more passwords than we remember, and we use managers to keep them, or we have our browsers remember them, or whatever. So how are passwords communicated? They're communicated over TLS. So they're viewed as application level material, as messages that are sent encrypted under the TLS session key. So it's not like the adversary is being handed the password through the communication channel. But nonetheless, there is the threat of dictionary attack. So if for some reason, somehow, an adversary obtains the image of the password under some public function, it's able to mount this attack. And indeed, obtaining such images is quite common and possible. And this leads to dictionary attacks being quite prevalent and successful. And of course, what makes dictionary attacks possible is that users are selecting their passwords poorly. They do fall in this dictionary. And you might say that the route to getting around this is that people need to pick better passwords. That, of course, is much easier said than done. And on the other side, attackers are getting better and better at making dictionaries that capture more and more things, right? So we do see protecting against dictionary attacks as important rather than assuming good passwords are going to be the norm. Indeed, for example, you can see on the internet through breaches, in fact, they will collect, what are the most common passwords. And the 25 most common passwords make up more than 10% of surveyed ones. And you can look at the types of things used across years, right? So the word password was the number one password in 2011 and 12. In 2013, the most common password was 123456. And that has apparently remained the case up to 2018. And so it goes, right? In the second most common password is the same, just some kind of permutation across the years. And then you see others like the keyboard characters, QWERTY. So of course that will fall in a dictionary, ABC123, names of animals, dragons, and trust no one. But, the attackers know about this and they will put it in their dictionary. Baseball, welcome, admin, sunshine, names. There's other interesting elements, which is some of these passwords do not look easily guessable, right? Some of them look quite random. Something like this. No, this one isn't random looking. That follows keyboard structure. I don't know if I can find one that does look pretty good. I'm having a hard time doing that, although I have in the past. But to cut a long story short, one reason that happens is that you have bots that are hardwired with certain passwords, and thus those passwords become common. Anyway, that was a bit of a detour because I think it's nice that we understand something about passwords in general. But coming back to how it connects with session key exchange, there's a goal called PAKE for password-authenticated key exchange. And the idea here is that the client and server have a shared password. It's the client's password, which has been communicated and sort of established and set up with the server. And they expect now that authentication and session key derivation is done under this joint shared password. There are two variants of the model. Sometimes the server has the password in the clear, sometimes it has its hash. For simplicity, we'll consider the first setting. The client always has the password in the clear. The goal of the interaction is that they arrive at a common session key, and that should be a true session key. It should satisfy as usual authenticity, secrecy, and now we want to add forward secrecy. But we want to add something more, which is security against offline dictionary attacks. What that means is that if an adversary sees or even is involved in interactions with one of these parties who own the password, it should not obtain information that allows it to mount the dictionary attack. Just for emphasis, note that we are not assuming that the password is well chosen and outside the dictionary. The password may be in the dictionary. If the adversary got the result of a public function on the password, the dictionary attack would be possible. So the goal of the protocol is to prevent any public function of the password being leaked through the protocol. Now, of course, as usual, one question here as well, what exactly is this security requirement? Can we define it formally or something like that? We can, but we're not going to take that route. And rather, we're going to look at this intuitively and say that roughly the idea is the adversary can observe any number of sessions between the parties, and it can also be active. It can try to participate as one of the parties in an interaction with the other party. But every time it's active and tries to engage in an interaction with one of the legitimate parties, the best it can do is eliminate one candidate password. We can't prevent it from doing that, because one thing it can do is pick a candidate password and just play correctly according to that. If it works, it got the right one. If it doesn't, it knows it got the wrong one, and that choice is eliminated. But it cannot, for example, through one interaction, deduce that now the following two passwords are not the correct ones. Okay. That is a little bit stronger even than the stated goal of not revealing a public function of the password, but it implies that. Now, a little bit of a change from before is that authentication here is mutual. The client is also authenticated, the server, not just server to client. And also, in this version that I'll illustrate, I don't want a public key infrastructure. Everything has to be done, authentication and key exchange, using just the password. Okay, so we could play with this. Let's see if we could create a protocol that is secure against dictionary attack. So again, what's the setup? Alice and Bob both share this password. And we're going to start with our prior DiffieHellman based session key exchange protocol, except that now B doesn't have a certificate or public key and hence doesn't have a signature. Alice picks its nonce as before, G to the A, sends that with its identity. The server responds as before, no signature, but it does include a MAC of the same quantities as before. Under what key is the MAC computed? Well, again, at this point, the DiffieHellman key L, which is G to the power AB, is known and can be computed by both parties. And M is defined as the hash of the DiffieHellman key, but also of the password, because the authentication now has to be done under the password. So at this point, B has to effectively prove, yes, I know the password associated with A, and that's what I'm using to authenticate myself. And that's done through making this MAC key depend on both of these quantities. And of course, a bunch of other stuff, but that other stuff is public. At this point, A also knows what L is. It checks the MAC, and then it acknowledges through another MAC with the same MAC key and on the same quantities. In case I didn't mention before, these prepended bits are simply to distinguish the MACs of A from the MACs of B. All right. As usual, the session key K is a hash of the DiffieHellman key, but now we also include the password in there, and we include all these for freshness and identity checks and so forth. All right, so we kind of know that this protocol may do pretty well with regard to forward secrecy and standard authenticity and so forth. But what about dictionary attack? Can you, in fact, mount a dictionary attack? And the question there thus is, can you recover a public function of the password from this anywhere? Now, you may think that this is not so easy, because if you look at this, where is the password used? It's used in this MAC. But this MAC does not appear to be a public function of the password, due to the presence of this L value over here, the adversary doesn't know what L is. And so if it has a candidate password, it cannot compute the candidate value of M associated to that candidate password. And so it's not clear how it's going to exploit what's here. But what that didn't recognize is, remember, the adversary is active. So here's what it can do. It will go to the server B and say, hi, I'm Alice. Here's my nonce, G to the A. Crucially, the adversary has itself picked little a and knows it. The server at this point just responds. It just thinks Alice is starting a protocol and says, okay, here's my nonce, here's my identity, here's my MAC. And the MAC we know is computed as before. This key M is the hash of the DiffieHellman key L and the password and other stuff. And the MAC is applied to all this stuff. Now there is a third flow going back from Eve, but we don't care about that because at this point the adversary is all set. It's going to mount its dictionary attack and retrieve the password. How does it do that? Well, it has the identities, it has G to the A and G to the B. And importantly, it has the DiffieHellman key because it knows little a. It can compute that as the adversary nonce raised to the power A. Now, let's consider the following function. On input the password, it returns this MAC. So it computes the MAC. The key here is the hash function h2 applied to all the stuff we saw before. That includes the DiffieHellman key, the password that's input here, and then the MAC is computed over this. In this function, we are regarding everything except the password as fixed. They're all determined through this one exchange. They're all public and known to the adversary, and they're all fixed. So this is a function of one argument, the password. But due to all these quantities being known to the adversary, this is actually a public function of the password. The adversary can compute F on any candidate password of its choice. Given that, since it knows the value of F on the target password, that's what's present in the flow over here, it has the means to mount a dictionary attack. It cycles through all the candidates, computes the function F on them, that's done quite quickly, just some hashing and macking, and compares to the value sitting here. And it will recover the password. So this is quite definitely not secure against dictionary attack. So as to actually changing that and getting something secure against dictionary attack, I'm going to leave that as a intriguing follow-on that you might explore if you feel like it. I'll just stop by saying that this has been a very rich area. The first protocols and idea of dictionary attack safe password-authenticated key exchange was by Belevin and Merritt in the early 90s. Provable security definitions and provable secure protocols began in the early 2000s. There's by now an enormous literature, a very large number of proposals with different quantity properties that you might explore. But one particular one I might recommend, because it's a modern one, is what's called the PAKE protocol. And if you want more information, the Wikipedia article on password-authenticated key agreement is pretty good. You'll find a lot here about the different variants of the problem, different protocols, the SPEAK protocol, the JPAKE protocol, Dragonfly, and so forth. Also, well, as these variants go, there's balanced PAKE, which means this is a question of whether the server holds the password in the clear or its hash. And they mention opaque over here. And if you want to look at opaque, you might look at the RFC. This is the draft standard for it. Or you'll also easily find pointers to the academic documentation on this.